Alright, so if you need your notes out from last night, the notes you took on that puzzle regarding chemical and physical changes, definitely have those. And I want you guys to talk about 1 and 2 the partner next to you now. Okay? Talk it out. And then write down some things so you can remember.
I told you, Ryan.
Triangle delta. It's fine. It's fine.
It's delta.
Alright, so I'm going to get some help from you guys, and I'll ask a couple more questions than just what's up here. So be ready for me. Alright, this group over here, you good? Okay. Bryce, what distinguishes a chemical change from physical? Give me anything you can think of.
Okay, physical is reversible, chemical is irreversible.
Okay, so physical would be reversible and chemical would be potentially irreversible. We say that up front because it's a generic way to help identify. Sometimes, though, later on in our chem life, we'll realize that this is just like 90% true. Okay, give me something else, Kendall.
Well, like a physical change is based more like on appearance or like a state change.
Okay.
Change like creates like a new substance.
Okay, so appearance would change potentially, and then we'd make a new substance. Those are kind of different things, but it's a great way to identify if something's physical or chemical changing. And then give me one more here. Ariel. Sorry. Say again? They, darn it. Okay. Now it's okay. Hold on. Come here. Let's think. Okay, so the new substance would also have new properties. That's one easy way to determine it. The physical change it can have new properties, but it's not so drastic. But like, for example, if I have a state change, I'm liquid and then I'm solid, right? Well, do you have different properties? Certainly, right? So I'm also going to put new properties here, but it's almost like it's an expected new property when you do a state change, but it's not an expected new property when you're doing a chemical change. So those are some great ways, okay? So based upon observations alone, why is distinguishing these changes not always straightforward? There's one in particular that kind of falls on both sides. It makes it kind of difficult to tell if it's a physical or chemical change. CJ, anything?
Like, chemical changes aren't always able to be seen, obviously.
Okay, so it would have to be, you know it's happening, but maybe it's not observable. So non-observable changes. There's one more. Yes, Mishka.
Like when color happens, I'm not sure which one. Physical.
Good. So physical, you can have a color change that is predictable. And then in chemical, we would have a unpredicted color change. So delta means change, okay? Delta means change. Okay. So in terms of predictability, if I have a glass of water and I drop some green food coloring in there, what color is it going to change? Green. Did you predict that change? Duh, right? You know food coloring is going to change the color of water. Is that a physical or a chemical change? Physical. So what did I end up making when I put this substance? Okay, so here's water, and I dropped a drop of green food coloring, and it's now in here. What did I end up making? I made some colorful water, but think back to the matter talk yesterday, one of those classifications of matter. What did I make? I made a mixture, and mixtures are physical combinations, not a chemical combination. So a mixture can be separated. Like, it's going to be hard, but I could get that food coloring out of the water through distillation. I definitely could, okay? But if I have a substance in its blue, we'll say blue, and I react it with something, and automatically it changes purple. That's my color I got right here. Okay, and it changes purple. I did not expect this reaction of a blue substance to turn purple. Okay, so that would be probably because this was compound A and I made compound B, so I made a new compound. And that new compound had the physical characteristic of purple, whereas the first compound had the physical characteristic of being blue. So I made something new, which happened to carry along with it a different color, and that would be an unexpected color change, so we call that a what? Chemical change, and because I've literally made a new substance B, which is now purple in color. So we're going to see some of these things happen in the lab. All right, so one more review of units with dimensional analysis as well. Okay, so take a minute to look at this. Solve. So get me started, Admir. What do you think about this first one? What is 25 degrees Celsius in Kelvin? There's a relationship that you guys wrote down on video 1 that you guys took on that puzzle. How do I get from Celsius to Kelvin? All right, you can pass on this one, but not the next one, okay? Let's go to Hannah. How do I get from Celsius to Kelvin? So Kelvin temperatures are Celsius plus 273. So if we had 25 degrees Celsius, what is that in Kelvin? 298 Kelvin. Good. Okay? And so if I'm going from Kelvin to Celsius, think about what I can do differently, Bailey. Subtract what? 273. So if I have 0 Kelvin and I subtract 273, what is that in Celsius? Negative 273 Celsius. And this is actually absolute 0. At this point in time or in temperature, what they say, those theorists out there, they say all movement stops. Because basically right now your whole body is vibrating. Because you're warm, right? Your body temperature is what? Fahrenheit, but you could convert that to Celsius if you wanted to, right? So basically, you could also convert that to Kelvin. But at absolute 0, all movement halts. And so everything's going to stop moving. And we have not actually achieved that. It's still a theoretical value. We've gotten down to maybe 100ths of a centigrade from that. But at that point, all movement would stop and you would die. Right? Well, eventually, anyway. So, all right. So joules is the unit of energy that we call out for the SI unit, but it's similar to something that you consume every day, which is calories. I'm telling you that conversion factor is 1 calorie is equal to 4.184 joules. Okay. So, who had breakfast not too long ago? Okay, what'd you have, Bailey? Bagel. Cream cheese? All right. So your bagel was probably what we would say, like on packaging, it was probably close to 300 calories. Okay, so this is a bagel. All right, so I want to know how many joules, J, are in these 300 calories. So this is our bagel. And then what would I start with here? What would I start with? Dimensional analysis. 300. Okay, so 300 calories. All right, Abner, what would I plug in here to convert this to joules? Where would it? So what am I plugging in unit-wise first?
You go to calories on the bottom.
Cal on bottom and
Joules on top.
joules on top, and then I'm trying to get to everybody if I can. Riley, what would I put number-wise? Say again? Riley, sorry, I'm working on where at though. Okay, so 4.184, and then what goes down here? 1. All right, so calculate, guys. Hopefully somebody's here at this point already. 255.8. And that's joules, right? Okay, so calories gone, joules are left. All right, so this is actually how many joules you ate, potentially, right? That actually is not a whole lot. Your body uses a whole lot more energy than this. So let me tell you just a fun fact before we move on to our lab. Little c calories are not what's in the packaging on your food. Has anybody like actually looked at their nutrition labels maybe recently? You should somewhat be aware of what you're eating just for your own health. So what you probably saw on the bagel packaging, if you looked at it, it would be 300 calorie, big C calorie. So we Americans don't understand that's different than little c calorie. What this actually represents is kilocalories. So kilo means 1,000 times greater than base unit. So this is actually 300 kilocalories. Okay? So if instead they put 300 kilocalories on our packaging, we don't use the metric system in America, right? Right, so we wouldn't know what that came in, but you guys do because you're now like intelligent citizens of America. So that's truly what you're eating is kilocalories when you see big C calorie. Okay, so that actually makes this not 300 calories. So that makes that what? 300,000 calories, okay? Which makes this what? 200, right? So just move the decimal over 3 places, which is 1.2 million joules, right? So basically what you're eating every day, it's like they say, oh, you're supposed to have about a 2,000 calorie diet. That's big C calories. So convert that to little c calories. Not a 200,000 calorie diet, a 2 million calorie diet. But if they told us we could eat 2 million calories, everybody would be obese. Because we're like, I got more calories than I got today. Like, to count my calories, I got plenty to eat. So what they do is they bring it down to a reasonable number. So if people are trying to watch their weight or stay healthy, they can manage that. Because you can imagine counting 2,000 versus 2 million. Like, that's a big difference in our minds of what we think about. So actually what you're eating is a lot more calories because your body actually uses joules or little c calories. We don't use kilocalories. Our body breaks it down to the smallest unit of energy, and we use a lot of it though. But your body needs that. Like if you're an athlete, your body needs probably close to 4 million little c calories, aka 4,000 calories. So your body needs it. So don't get me wrong, but they do lie to us. They don't think we're smart enough to understand. So that's my plug for the metric system. Okay, so this is homework you're going to approach tonight, so I'll tell you that now. So you read about and you looked over chemical and physical changes. We're going to talk about it more in the lab today. So homework, it says online chemical physical changes homework. It's like a Google form. You go through and you do check boxes of what's chemical and what's physical, and then you label things that are chemical and physical changes. So it kind of looks like this, and I'll pull it up for you guys shortly. So we're going to do our lab now. We're doing 2 labs in 1, okay? And pull out the reading guide sheet. Everybody, the reading guide sheet has a data table right next to it. I think it's that one. So tear that in half. Because I do not want your reading guide. I only want you to have that data table with you. So just, crease it really well and tear it in half, or lick it and tear it in half, or I can throw some scissors at you if you need to. Yep.
Yeah.
So that is just me trying to be nice to give you a data table to work in, so you don't have to draw your own data tables for everything. I try to do that because I have some people who will spend like half an hour drawing a data table and never actually get to the lab, okay? So if you're already making a mess of your tearing job, you got it?
Yeah, I think so.
So you crease it really well, you can tear it. Strengthen your immune system. All right, so eyes back up here for me. Here like ninjas so I can talk over you. Okay, so the two things we're doing. First, we're learning how to light a Bunsen burner. Yay. I will have to demonstrate this for you step by step so that we're all on the same page. So don't get ahead of me here, because I'll have to kind of stop the lab and make sure we're all on the same page. Then we'll do the chemical and physical changes lab. You maybe have done something similar to this in biology, so you have some background knowledge, but this is going to approach it just in a slightly different manner. So we have to wear we have to wear what? The most important piece of safety equipment. Goggles, okay? If you want to wear an apron because you got like a nice shirt on or something and you're like, oh no, I need my shirt, then you can wear an apron. I only have a couple over here underneath this goggle cabinet here. And you must wear what? Closed-toed shoes, okay? So I don't see really anybody with sandals, so making sure that's there. You need to share the materials because at each station I have one bucket full of materials, so you have a lab station across from you, so just, sharing is caring. And then scoopulars, those are the scoopers, right? Make sure they are clean. They're not like contaminated with something, so wipe it off with a paper towel if that's what you need to do, or actually wash it. We will be using matches, okay? So matches, when you blow them out, what do?
Smoke.
They smoke, right? I don't want smoke up in this room because the carbon dioxide detector will go off. So I'd like for you, right, when you get back there, is get a 100 milliliter beaker, just a small one, fill it up with water. So instead of, you strike the match, you light whatever you're lighting, don't blow it out, okay? You just dunk it in water. Okay, so that's what your beaker is going to be used for disposal of matches, so it just does not smoke up the classroom. Now, I'm going to leave this on the board, but I guarantee you'll forget little bitty things, okay? So maybe right on your top of your paper on the back, beaker of water. And I just have a couple other things I'm going to tell you up front so that we're on the same page. In step 3 of the lab, you are going to put sodium chloride in a test tube. You're just going to shake it lightly because then it says show Miss Enlow. It might still say in the lab note show Miss Smith. That was my maiden name, sorry. But you'll just shake it lightly. And then after that, you're going to put in some silver nitrate. This is in your bucket that are provided for you in the lab stations. In the lab, it says like a full pipette or something like that. 5 drops will do. Okay, so step 3, 5 drops. Because that stuff's like $100 a bottle, so I just try to be somewhat conservative. So just try to stick around 5 drops of that. So a pipette, you literally just do drop, 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 drop. Okay. Step 4, I have already done a change. So this is the chemical physical changes lab. So turn back to the data table on the front. Do you see it says, like, describe, let me look over someone's shoulder. Describe what substance underwent the change. So you literally will describe the substance, so like what it is, the candle, the piece of paper, the magnesium ribbon, whatever it may be. And then you label it as C or P, and then you go on and say why. So you have to describe it in technical terms. So don't just say, I cut it. You're going to say, it changed shape. It changed size. It changed somewhat of its appearance. Gas evolution. What are some more chemical changes? Say again. Flammability is a property, not a change. Okay, so say again.
Precipitate.
So precipitation is a form of a chemical change. Gas evolution. What else? Say again. Rusting. So if something rust, you would say it was oxidized. It would change color, which is a new substance that it's been formed. What else? Fizzing. So that's gas evolution. What else? Look at your notes, because if you put 4th grade terms on here, it will not be correct. You want to try to use your vocabulary, use the correct phrasing. Combustion, which to you means fire, right? So you could say combusted and made flame, which is the flame is not the new substance, the carbon or whatever, the positive form is the new substance. Okay, so if you need to look at your notes for that description part, the evidence or observation, that's going to be something you definitely can use. Okay, so don't just put cheesy things. Try to make them like legitimate technical terminology, so you know you're practicing. So on step 4, do you see 4 on your paper? Okay, I have done this for you. I took a piece of magnesium ribbon, and it's really long, like a long piece of ribbon, and I cut it into little pieces. So what did I do for you? I did a what kind of change? A physical change. So you might want to write that part down, because I had to go ahead and cut it so I could distribute it to your lab groups. So I will provide for you at your lab station 3 pieces of magnesium. There's like little pieces of metal, and you'll drop 6 molar, which is like a really concentrated hydrochloric acid. So I will give you like very concentrated hydrochloric acid in dropper bottles, and you'll drop about 8-ish drops on those magnesium ribbon pieces, and you'll look for a change. Okay, and you'll hold that with the test tube holder or keep it in your test tube rack, not just like hold it up to your, don't hold it up to your face, don't hold it with your hand. Sometimes you don't know what's going to happen, so don't hold your hand around a test tube all the time. And then at the very last step, we'll all kind of be on the same page, and I'll demonstrate this for you, but you'll be actually using the Bunsen burner at that point, and you will, let me show this to you. You'll take a Bunsen burner, you see this set up a little bit better now? Hold a test tube with the test tube holders at an angle over the top of the Bunsen burner, not hitting like right in the flame, but kind of above the flame some, and you'll look for changes happening in that test tube. Okay, so at that point, we'll kind of all be on the same page though. All right, so major questions right now. It's a lot. Okay, so hair back, closed-toe shoes, goggles on. Meet you in the lab stations in just a second with your lab notebooks out. Okay, same lab groups. Go. So if you have hair, put your hair back. If you need a hair bow, I got like 1 or 2. Okay, hold on.
Is this good?
I'll just use clips. Or tuck it in your shirt or something. Your hair should not be out and about. Alright, lab notebook out. Pull out the Bunsen burner. How to light a Bunsen burner lab. Somebody needs to get goggles. How to light a Bunsen burner. Let's go. How to light a Bunsen burner. Time to lab. You have about 3 seconds to get settled. Nobody can sit right now. Get up. You can sit all the rest of the day. Alright, 3, 2, 1. Stop moving. Okay, thumbs up if you tell me how to light a Bunsen burner. Alright, cool. So, I'm going to work at this group for, actually, I might. Okay. So at this point, I will start passing out, send somebody to me to come get a striker. I just have to make sure the flames are good. So 1, 2, 3, do not strike this yet. Do not strike this yet. Just kind of grab one. That was me. Okay, so I think it's a good one out here. Okay, guys, so you guys stop moving from me, okay? So is everyone striker? Okay, so at this point, I'm showing you the 4 steps on how to light a Bunsen burner. So if you guys can't see over there, just scooch. So everybody, just follow along with me, and then be able to stop in between steps, okay? So the Bunsen burner. So the Bunsen burner is going to go on the gas jet. The gas jet is at the perpendicular position right now, meaning it's not on. By turning the gas jet on, you hear the gas. It's not always on. I just turned it on before class. So that's what we always trying to make sure we're not playing with. So if you're allergic to latex or rubber, don't touch the end. Somebody else can. So everybody follow along with me. So go to your stations. We're going to take the gas, the latex end, put it on the gas valve. About halfway up, you have to get it on. Put it on. Alright, back to me. 3, 2, 1. If you didn't get it on there yet, we'll get it on there in a second, okay? Alright, so that's step 1. Step 2, you're going to look at the butt. Look at the butt. Alright, so you guys know how righty-tighty and lefty-loosey works, probably this point, right? So the gas inlet valve needs to go righty-tighty all the way. So we're going to go righty-tighty. We're going to tighten it. Don't tighten it so down that you can't get it back open. So it's just closed. That means no gas will come through. Alright, so the rule of thumb is now look on that lab. It says turn the gas inlet valve how much? 180 degrees. How much of it turns 180 degrees? Half turns. What do you want? Alright, so 180. So all you're going to do is put your hand on there and you're just going to go half wrist turn. Go. Half wrist turn. And if you go a little bit more than 180, it's fine. Do not go 360. Just a little bit more than 180 is fine. Alright, so the butt has been taken care of. That's the gas inlet valve. That's the gas that's going to come out of the jet in here. Now you have the barrel to work with, and the barrel has like a gap in it, and that's just for oxygen coming in, because fire needs oxygen to fuel, right? So we're looking down the barrel, usually bad option, but we're looking down the barrel, righty-tighty all the way. Righty-tighty all the way. Follow along with me, let's go. Righty-tighty all the way. Close that thing all the way down. Because you don't know if you set this up before you, and if they're a good crayon or not a good crayon, okay? Alright, so it's closed, no oxygen will come in. Is that going to let the fire light? No. Okay, so what does it say? We need to turn it how many times?
4 complete turns.
4 complete turns. Now, I can't turn my wrist all the way around, so I'm going to do 8 half turns or 4 complete turns, okay? Open, lefty, loosey. Alright, so at this point you have 4 complete turns on the barrel. You get thumbs up if you have a little bit of a gap now between like the screw section and the barrel. There's a gap. Okay, so now we have enough gas coming out of our jets when we get there. We have enough oxygen to fuel it. What's the last thing we need to make a fire? The splint, or the flint from the striker. Okay, so the way this works is one of your partners will be turning on the valve, which is going to be not the perpendicular but the parallel position, and the other one is going to put their thumb, so most of us are probably right-handed, I'll just the lefties in a second. Your right thumb goes on the left metal prong, I guess is what else to say, okay? And then you're just going to push towards you, so you're depressing in and depressing over at the same time. Get a strike. Just go once. Get a strike. Get your power on. I'm here. Right. And so here's the problem. So stop signs for a second. Some of you guys would just get lazy and say, like you're still like this. You're not pressing the flint in. Because the flint is this little piece and you need to strike with some pressure. So let everybody try right now. Everybody try. So you press some pressure. Okay, good. Everybody needs to get it straight. So after you actually get everybody try. Alright, you hold down for 4 seconds and make sure you can strike. Alright, so at this point, put the striker in one person's possession. Okay, one person's possession, you know who would like the best. Alright, we are not going to finish the battle, you guys are not with me. Okay, so one person's going to then turn the gas on. They're going to count down for me, 3, 2, 1. So hold on for just a second, I'm going to show you this first, and then you guys can do it, okay? So turn the gasket on, they're going to count down 3, 2, 1. You're going to count down for me. 1, 3, 2, 1, 3, 2, 1. Parallel, and I'm going to strike. So if I can get in 1, 2, 3 strikes, I'm out. She has to turn it back off. We're just gassing the room. Got it? You have 3 strikes. Get it out. Go.
Turn it off, turn it off.
So guys, one answer is not going to be.
Oh, that was three, two,
Let me get this. Why is your plane going so slow? Dude, look. Why did you guys turn on? Why?
bro, you gotta let it flow.
Alright, so follow the lab. Follow the lab. It tells you want to try to see what a yellow plane does, a blue plane does. Follow the instructions in the lab.
Remember that time?
Alright guys, I want an inner blue cone right now. Get an inner blue cone. Follow the Bunsen burner lab. I want to see an inner blue cone. I want to see an inner blue cone. No yellow. No yellow.
No yellow.
Blue.
Dude, that's yellow.
Let's go, Brian.
This still needs to be adjusted. This needs to be adjusted. No. These are the only things you adjust now to make it an answer. Go. So you guys can make a lower place. No. That's not all million adjusted. Can you lower your gas now, so turn this down?
Alright, Ian, listen, 5, 4, 3, 2, 1. I see most of you guys have an inner blue cone. You realize now the gas inlet valve, the bottom is what's going to make the flame high or low. And you notice the oxygen is what's going to make the gas, the flame yellow or blue. You adjust the oxygen to make the gas turn blue. I mean, the flame turn blue. The blue point on the inner blue cone is the hottest part of the flame, and that's generally something we'll need for some of our reactions. Okay, gas off now, so turn it off from the perpendicular, from the parallel to the perpendicular, and then now go ahead and read the chemical and physical changes lab. Look at the purpose.
We'll get this in a second.
And then again, again.
Water too, right?
Read it, and begin getting put it out. Read Stop striking.
Good job. That's gonna fall. That is definitely
Keep it there.
Oh, the candle's melting.
So it's me. Right?
Alright, so as you are starting, listen up, 3, 2, 1, I do like to kind of make sure we're on the same page. You are starting, you're doing all these little operations with your hands. Are you thinking, what is chemical and what is physical? Because every single step, step 1, there are at least one chemical change and one physical change. As you make the observation, fill out your data table. Then you may move on to step 2. Look for the chemical and physical changes. There's at least one chemical and one physical in each step you do, okay? Talk to your group and make sure you get it completed before you move on to step 2.
It's something with the heat. No, it's how we look at the
These are very small.
Yes, you will forget your observation when you make observations at home.
That's what it says. Okay, 2A.
Alright, step 1 is done. If your candle is still burning, go ahead and dump that candle in the water and you can start step 2.
Don't want any fires in here.
Candle, step 1 is done.
When the people bury
Alright, so your small haystack is on the watch glass. The watch glass is kind of away from everything else. When you're ready to put your watch glass fire out, you can use your watch bottle. That is the blue watch bottle. Do not blow your fire out. Blowing the flame will blow the paper.
That's a physical thing.
Wait, is this how she said to do it?
All right, you are using a graduated cylinder to measure. Test tubes are worthless. They don't have any graduation on them. You're using a graduated cylinder. So here's how you guys make sure it's on the top. So all you do is you pull it stronger with one hand, and you go straight to the side, you see how it's on the bottom. In this minute, make sure all the before you start tasting. There should be a pipe right in here.
They just use that, they just use that.
I'll show you another way.
And then straight to the side until all the salt, there's a lot of salt in there. So half the salt. And then you can learn to do it.
Was yours guys just white?
Okay. Now we're on.
Dude, it's so nice. Back in the bottom. That's in my eyes. I just touched the top of it.
I don't know. Did you actually?
You're at the bottom of it, guys. Oh my gosh, you're so hot. You're the bottom. You're the bottom. It says to on the sheet. You're the bottom of the
Yep, and it says 8 drops. See if they're No, then that's not it. I'm sorry. Put that one away. Yep, put that away. I thought you were on the next step. It's silver nitrate. You see the silver nitrate? No. Look for something that's.
Oh my god. Hold it. What? I knew
Where's that roof?
All right, so everybody, just gonna pause for just a second. If you're in the middle of something, just put it down. This attention. Some of us are ready to move to step 5, so others are not. That's totally fine. We've got time. But step 3 and 4 make some solids right in your test tubes, and I don't want you to put any solids down the drain ever. So I've provided you with a piece of filter paper. So there's one per table. Okay, so I need the combination of efforts here. I need a beaker out, a funnel out, and someone hold up a piece of filter paper. So one per table. One per table. One per table. Okay. Alright, so a beaker, not a flask, a beaker. Try this again. Beaker, make sure your funnel fits in your beaker. Alright, so hold up the funnel, the filter paper. Okay, so take the filter paper, fold it in half. Okay, so take the filter paper and fold it in half. And then fold it in half again, so you're making like a triangle. Yeah, I do a triangle, okay. So you got this, okay, so see how I make it kind of a tight fold. Okay, and then now you're putting it back up and you have like a little X in the middle, right? Okay, take 2 fingers on like one fold and like halfway away from another fold. And you're just gonna fold it on top of itself in such a way you can make like a little bowl. Okay, this is not pretty. Okay. So after I folded it on top of itself, I make a little bowl. Like so. Just make a little bowl. Perfect. Little bowl. And it goes right inside the bowl. Alright, that is your filter, and that filter is used for anything liquid solid mixture. Any liquid solid mixture. Now continue where you are. I'll get you a comment. Let me know. Yeah, because really, yes, you're not like one. like hanging, hanging around. So you make your observations on this, right? And then we let go. So you, instead of knocking the glass on the glass, you use a washcloth. A washcloth is a way Alright, we are cleaning up before step 5. You need to move on to step 4 if you're not already finished. I just like to, I thought you was the white, but like I was Clean up as much as you can before you start step 5, and then I'm going to make sure we're all on the same page. Alright guys, listen up over here, turn this way, just hold for what you're doing for a moment, I want to make sure you know how to approach step 5. Most of us are getting there. Alright, so eyes up over here. You got time, eyes up over here. So this group's going to show you a demonstration how to set this up. They set their Bunsen burner, they lit it, they have their blue powdered substance in the bottom of their test tube. Some of us are going to have bigger or smaller amounts just because of, I put on there 25 centimeters of needed to do conversion, but just a little scoop of the copper sulfate in there, so we just reach up, and then they're going to hold it at an angle above the flame. So all they're doing is they're not holding it at the face of the partner, because face of the partner are recorded, and they're going to hold it at an angle, and they're going to look for changes. They're not going to hold it directly in the flame, it's above it, it's maybe by an inch. Okay, so that's it, move on.
No, you didn't.
Guys, three strikes and you're out. Please do not strike the striker. Just for kicks and giggles.
Yes, that's why she said go home in my face.
Wait, hold it.
You made your changes, yeah. So the very last read instructions, okay? So what are some changes we understand?
Yeah, just read the word. So yeah, just like hold it as lightly as you can. Don't let go of it. Okay, when you want
Yeah.
Alright, at this point, all Bunsen burners are gonna be off. All Bunsen burners are gonna be off. You should have seen the changes you need to see. Let that baby cool down for maybe a couple minutes. And then don't forget to do the last step in step 5, that everybody needs to be concluding. The labs are gonna be going in the box in about 10 minutes. And cleaning, including cleaning. Do not take the Bunsen burner off yet, because there's glassware on your desk and you'll fling it off the desk. I've done it before, okay? So do not take the Bunsen burners off until everything is up. It's stronger than it looks. Can I see the link? For this school, right?
Okay, so what is?
Sorry, whatever we does, we can't, but sometimes there's times I don't I want to answer the You don't have to get the water out, it'll dry.